Printed circuit boards, PCBs, are the foundational building blocks of all modern electronic devices, from smartphones and computers to industrial automation systems and medical instruments. Despite appearing simple, a PCB goes through a sophisticated, highly controlled manufacturing workflow to ensure precision, durability, and electrical reliability. This video explains the 19-step PCB manufacturing process, outlining each stage in detail to help engineers, electronics hobbyists, and manufacturers fully understand how PCBs are made. Pre-production engineering. Before any physical production begins, engineers perform design for manufacturability, DFM checks, verify the Gerber or ODB++ files, confirm material selection, and generate tooling and imaging data. Panelization and drill files are also prepared to optimize workflow and yield. Inner layer imaging. The copper-coated laminate for the inner layers is cleaned and coated with photoresist. Then, using UV exposure, the circuit pattern is transferred onto the inner copper layers. This imaging step defines the pathways of the inner circuitry. Etching. Chemical etching removes unwanted copper. Only the copper protected by the hardened photoresist remains, forming the intricate internal circuit traces. After etching, the board reveals its completed inner copper pattern. Photoresist stripping. The hardened photoresist used during imaging is stripped away, exposing the clean copper traces that will form the inner circuitry. Inspection and post-etch punch. Automated optical inspection, AOI, checks for shorts, opens, and pattern accuracy. Alignment holes, post-etch punch, are created to precisely register layers during lamination. Alternative oxide coating. An oxide or micro-roughening coating is applied to the copper surface to improve adhesion between the inner copper layers and the pre-preg during lamination. This ensures strong bonding and structural integrity. Lamination. Multiple layers, copper foils, inner layers, and pre-preg sheets are stacked, aligned, and laminated under high temperature and pressure. This process melts the resin in the pre-preg and permanently bonds all layers into a single multi-layer PCB structure. Drilling. High-speed CNC drilling machines create vias, through holes, and component mounting holes. Microvias may be formed using laser drilling for HDI, high-density interconnect, PCBs. Drilled holes form pathways that will later be metallized. Metallization of the dielectric. The walls of the drilled holes are non-conductive, so a thin, catalytic copper layer is deposited through electroless plating. This seed layer prepares the holes for full copper plating and enables electrical conduction between layers. Outer layer imaging. The outer copper layers undergo the same imaging process as the inner layers. Photoresist is applied, exposed to UV through the outer layer phototools, and developed to reveal the pattern of external circuitry. Copper plating. Electrolytic copper plating thickens the outer traces and builds up copper inside the drilled-through holes. This creates solid electrical connections between layers and ensures the durability of vias and pads. Photoresist stripping, outer layer. The photoresist used to protect the copper during plating is removed, exposing both the plated and unplated copper regions. Final etching. Chemical etching removes unprotected copper from the outer layer, leaving behind only the plated copper that forms the final surface circuitry of the PCB. Tin stripping. The temporary tin coating used as an etch-resistant mask is stripped off, exposing the finished copper traces. Solder mask application. A layer of solder mask, usually green, but available in many colors, is applied to protect copper traces from oxidation, prevent solder bridging, and provide insulation. UV exposure defines openings for pads, vias, and test points. Surface finish. Surface finishes protect exposed copper pads and ensure excellent solderability. Common finishes include HASL, hot air solder leveling, ENIGA, electroless nickel immersion gold, OSP, organic solderability preservative. Immersion silver or tin. Each finish offers different advantages depending on cost, complexity, and application. Silkscreen printing. Component labels, polarity marks, logos, and reference designators are printed on the PCB using silkscreen or inkjet printing. This step assists assembly technicians during the PCB assembly process. Electrical testing. Using flying probe testers or bed of nails fixtures, PCBs undergo electrical continuity, isolation, and netlist testing. This ensures that all circuits match the original design and contain no shorts or open circuits. Routing and V-scoring. Finally, the PCB panel is cut into individual boards using CNC routing or V-scoring. Routing cuts out the PCB's shape, while V-scoring creates break lines for easy separation during assembly. Conclusion. Manufacturing a PCB is a sophisticated multi-stage process that requires precision engineering, advanced chemical processing, and reliable quality control. Understanding these 19 steps gives engineers deeper insight into how a raw copper-clad laminate transforms into a high-performance electronic circuit board. Whether used in consumer electronics, industrial equipment, medical devices, or aerospace systems, the quality of the PCB manufacturing process directly impacts the reliability and performance of the final product.